You've turned every sentence into a point in 768-dimensional space. But now comes the real question. How does a machine know which points are close to each other? When someone searches how to cook biryani, how does the system find a document about dumb biryani and not one about quantum physics? There are three rulers for measuring similarity between vectors. Each one sees the world differently. Let's start with the most popular one, cosine similarity, the angle measurer. Cosine similarity measures the angle between two vectors. It doesn't care about length, only direction. Take two vectors pointing the same way, one short, one long. The angle between them is 0, so cosine similarity is 1 perfectly similar. The formula is simple, dot product divided by both magnitudes. Here's the code. Just 3 lines of num. Vectors A and B point in the same direction but have different magnitudes, and cosine similarity returns 1, meaning identical meaning. This is why it's perfect for text. It captures semantic direction while ignoring how long the text is. Next up, the dot product, the magnitude-aware scorer. Unlike cosine similarity, the dot product cares about both direction and magnitude. A longer vector gets a higher score. Watch, vectors A and B give a dot product of 0.5, but vector C, same direction as A but 10 times longer, gives 2.5. When does magnitude matter? Think product recommendations. If the vector length correlates with popularity, you want the dot product. It naturally boosts popular items that are also relevant. Cosine similarity would ignore that popularity signal entirely. Third ruler, Euclidean distance. This is the straight-line distance you learned in school, the Pythagorean theorem extended to any number of dimensions. One critical difference: lower distance means more similar. That's the opposite of cosine similarity, where higher means more similar. Here's where it gets interesting. Let's see where these metrics disagree. Take 3 sentences. A is I like cricket. B is I like cricket, repeated 3 times, same meaning, longer text. C is I enjoy tennis, different meaning but nearby in space. Cosine says B is most similar to A. Euclidean says C is closer. Same data, different answers. Now here's a secret most tutorials skip. If you normalize your vectors to unit length, all 3 metrics become mathematically equivalent for ranking. And guess what? Most modern embedding models, OpenAI, Cohere, Nomic, return normalized vectors by default. So in practice, cosine similarity equals dot product. But there's a trap lurking in high dimensions, the curse of. In 2D, random points cluster naturally. But in 768 dimensions, all pairwise distances converge to nearly the same value. Look at this. The ratio of standard deviation to mean distance drops from 0.38 in 2D to just 0.018 in 768D. Everything looks equally far apart. This is exactly why trained embeddings matter. Random vectors are useless in high dimensions, but models like BERT and OpenAI's embeddings learn to place semantically similar text in nearby directions, creating meaningful structure in that vast 768-dimensional space. So which metric should you pick? Here's the decision tree. Are your vectors normalized? If yes, use dot product, it's the fastest. If no, use cosine similarity for semantic search and RAG dot product for recommendations where popularity matters and Euclidean distance for clustering or anomaly detection. Let's prove it works. Here are 5D embeddings for king, queen, and banana. King and queen have a cosine similarity of 0.99, nearly identical meaning. King and banana, negative 0.18, completely unrelated. The math genuinely captures meaning. Let's recap. Cosine similarity is your default for text. It measures direction and ignores magnitude. Normalized vectors make all metrics interchangeable. Dot product is the fastest when vectors are normalized, and Euclidean distance struggles in high dimensions but shines for clustering. The 90% answer? Just use cosine similarity. Next episode, we tackle the real challenge. You have 10 million vectors and need the 10 most similar ones in under 50 milliseconds. Brute force comparison won't cut it. Enter HNSW, the algorithm that makes vector search feel instant, even with billions of vectors. Subscribe so you don't miss it.